The story of Voyager communications begins with Motorola in Scottsdale, Phoenix, Arizona, the Government Electronics Division. The term Six Sigma is copyrighted by Motorola. The Six Sigma concept was introduced by engineer Bill Smith. Sigma is a statistical unit of measurement that describes the distribution about the mean of any process or procedure. A process or procedure that can achieve plus or minus 6 sigma can be expected to have a defect rate of no more than 3.4 defects per 1 million opportunities for failure. That is a reliability rate of 99.99966%. Six Sigma is achieved by proper circuit design, component selection, component reliability, component sourcing, quality assurance, and system integration testing. For space communication systems, as used on the Apollo spacecrafts and the Lunar Landing Module and the Service Module, and in the case of transponders for the Voyager spacecrafts, system reliability must go beyond Six Sigma. Motorola design engineers Scotty Miller and Larry Brown of the Scottsdale, Phoenix, Arizona Motorola plant designed the communications systems to have a 1 in 1 million failure rate. That is a reliability of 99.99990%, which goes beyond Six Sigma.
So what does it take to track Voyager 2? A big antenna. So in the case of this 70-meter Deep Space Station 43, so we can track on smaller antennas. We have a couple of beam waveguides that are 34-meter, but if you want a nice signal with a lot of margin, you pick a big antenna. So looking at it, you've got 8,000 tons, 4,000 below the bearing, essentially 4,000 tons at swivel. It's all hydraulic. 43 is a hydraulic antenna, and it uses a unique platform called a hydrostatic bearing. So there's no friction. So the whole antenna that moves rides on a film of oil 7/1000 of an inch thick. Pressurized to 2500 psi, it just lifts it a tiny amount and it slews round. At the moment we are looking at Voyager 2 we're tracking now. The beam width of the antenna on X-ray band 30 millidegrees. So if we deviate any further side to side we lose it. So in fact it's not just the antenna pointing that's the important thing, it's the subreflector as well. The subreflector sort of moves on all axes, and we actually have calibration tables that, so as the antenna goes down we have a squint factor where essentially the antenna will sag, and it has to be compensated for as well. Now that's just the antenna side, so we have, obviously that has to be extremely accurate. Then we also have the RF side, and that's where the interesting stuff comes in.
The Voyager spacecraft were launched from Cape Canaveral, Florida in the late summer and early fall of 1977. They are supplied with electrical power from radioisotope thermal electric generators, which generate 249 watts of electricity. So they don't need the sun. And these things are still transmitting to this day in 2020. They are being programmed, transmitted to, and received by radio dishes in Australia.
So this one is the bread and butter transmitter. This is used on a daily basis and communicates from everything from New Horizons, which is on the way to the Kuiper Belt, to Mars. Anything closer to the moon, 70-meter can't do. The beam's too tight. So certainly sort of Mars and beyond. And in fact, so you start talking about K-band. This antenna is only K-band capable on radio astronomy. The beam waveguides now are K-band capable for spacecraft. And we have a spacecraft called LRO, which is a lunar. When it points to Earth, it has to point to us on K-band. Otherwise, we don't receive it. So even on the spacecraft with K-band, the beam is narrow. but on a 34 meter, it's narrow as well. So yeah, unless the two are pointing physically at each other, it's almost like a microwave repeater. Now, the teams, we'll have teams of 5. Oh, this is my desk. So it's a new desk. It's a very special desk. It has lots of screens. So essentially this also allows me to interface with our flight systems as well. So I can from here call up anything on the other workstations. If you pan around, essentially each workstation here can incorporate 2 antennae. So we can have one of our controllers controlling Deep Space Station 35 and 34 at the same time. So it could be Mars, it could be, in the case of what we're tracking now, we're tracking on Deep Space Station 43 Voyager 2. And so on Deep Space Station 34, we're tracking wind as well. So as the day goes on, we have the Mars rising, and I'll show you the schedule that we have. So this is our tracking schedule at the moment. So you'll hear some noises at the back. They're just doing testing. So everything in green is essentially what's being supported now. Deep Space Station 43 is tracking Voyager 2. There was a command uplink as well. And as we just described earlier, so we did the best lock frequency and transmitted a number of no-op commands to the spacecraft as well. Voyager, as I said, has a great big high gain antenna. It has a 20-watt transmitter, which doesn't seem huge, but it seems to be ample for what we need. So the 158 is fairly good. Carrier residual. Now, this is not, at the moment we're not coherent, which means that the spacecraft is using its US end. It's an ultra-stable oscillator, so it's its own time reference. But even over 15 billion kilometers, we're only 183 hertz out.
That's crazy.
So predicted, we're pretty well bang on.
As Voyager 2 speeds by the planet Saturn, sending back pictures from more than 1 billion miles away, Motorolans at the Government Electronics Division, GED, in Scottsdale, Arizona, have more than just a passing interest. The GED people developed the radio frequency subsystem on board the spacecraft, which is the transmitting information from the Saturn system to scientists at the Jet Propulsion Laboratory in Pasadena, California. But more important, much of what scientists are seeing they didn't plan on a year ago. Voyager 2 is concentrating on selected targets which JPL scientists chose based on information from Voyager 1's Saturn encounter last fall. That was long after Voyager 2 was programmed and left Earth, so it had to be reprogrammed during flight when it was closer to Saturn than Earth. Telling Voyager what to do is the main function of a Motorola SX band transponder, the major piece of equipment in the RFS. During the cruise phase, or when the spacecraft is traveling between planets, the RFS receives instructions from Earth and transmits them to the computer brain of Voyager. On Voyager 2, the transponder allowed scientists to guide and correct the course in order to concentrate on different areas of the Saturn system than originally intended. Photography of the moon Titan, for example, has mostly been replaced with additional photography of Saturn's rings, especially the braided F ring. The braided ring really startled scientists here on Earth, said Bill Arnold, Marketing Manager, Aerospace Electronics Office of GED. Much of what we thought we knew about the physics of the solar system was turned upside down. The RFS was designed and built to communicate course correctors to Voyager 2. But those corrections became even more important with the discovery of the braided ring. Obviously, scientists want to get as good a look at it as possible. Voyager 2 has been corrected to approach Saturn from above the ring plane, with the Sun behind the spacecraft. Observations of the rings are entirely on their sunlit side. At its closest approach to the planet, Voyager 2 will be 69,000 miles above the planet's dense clouds and only 2,000 miles above the outermost G ring. The other main function of the RFS is transmitting information. As Voyager 2 travels past Saturn, the RFS takes input from the spacecraft's highly sophisticated camera system and sends it back to Earth as X-band radio signals. On Earth, the RFS signals are electronically transformed into photographic images. This is how the RFS helps scientists see more than 18,500 photos of Saturn Voyager 2 is taking. In addition, the RFS will keep scientists here well informed of the velocity and position of Voyager 2 as it leaves Saturn's system and heads for its January encounter with the planet Uranus. Voyager 1, which took pictures of Saturn in November, is headed on a different course. Voyager 1 is now bound out of the solar system, searching for the supposed boundary of the heliosphere that separates our system from the rest of the cosmos. And if it finds it, another Motorola RFS on board will tell it what to do.